Okay. So good evening, everybody. It's a great pleasure that you're all back to this event. So we actually shifted the program such that we have this colloquia once a month, so every first Thursday of the month. So we will keep you posted, of course, for the next talks. Anyway, today we have the great pleasure and honor to have Juan Garrahan as a speaker. He is a professor in the University of Nottingham and has for a long time already been at the forefront of trying to understand non-equilibrium physics, but also glassy physics. Lots of very original and interesting contributions, and we are really looking forward to his works that are related to tensor networks and his talk that he will give us. So please, Juan, the stage is yours.
Thank you very much. I'm really delighted to be here, and this after dinner talk. And so I'm assuming everyone can see the slides and hear me okay. So yeah, what I'm going to talk is about recent work we've been doing, trying to connect ideas from tensor networks, specifically matrix product states, to the quantification of rare events in classical stochastic systems. So this is trying to connect, of course, the methods that emerged in quantum many-body to classical stochastics. You'll see what I'll talk about. The ideas about matrix product states or the methods are relatively simple for you. Many of you are experts on this in the audience. You will find them kind of very standard. But what I hope is that some of the application you find novel. So this is my plan, and please stop me as whenever you want if something is not clear, and I'm happy to answer questions at any time. So what I plan to do is first give some background, some recap about stochastic dynamics, rare events, atypical dynamics in stochastic systems, and I will focus just to have something specific, some class of problems, a specific class of problems to consider on kinetically constrained models, on classical stochastic models on lattices, one-dimensional models that have constrained dynamics, and those models have interesting dynamics, and to understand those dynamics you need to use these methods. And then the bulk of the talk will be about applying methods from tensor networks, numerical methods, matrix product states to these systems to study three things related to rare events. The first one is long-time dynamics, and that's the regime of large deviations, and this I will explain. And then moving to finite times, not long times, but times which are not necessarily large compared to correlation times. And then the third topic will be that of optimal sampling, how to sample rare events, optimally, or as optimally as one can. And this is work with Luc Kauser, who's my student in Nottingham, and Mari Carmen Bañuls, who's both of them I think are in the audience. And I will talk about these three more or less recent papers that we've written together, and there is one that will hopefully appear soon. And then if there is time, I'll basically say some words, rather than just applying methods, try to say some words about connections between continuous matrix product states and trajectory ensembles in stochastic dynamics. But we'll see whether I have time to get there. So let's think of, if not the simplest, one of the simplest stochastic systems you can imagine, just to set the scene. Imagine you have a particle hopping unidirectionally on a lattice with boundaries on matter, let's say periodic boundaries. It's hopping on a ring, and this is purely classical. There's a single particle that's hopping, and the hopping rate is gamma. So what it means is you have a continuous time Markov dynamics where the particle is waiting for some time, and at some random times that are controlled by this escape rate gamma, it hops one side, and then it keeps hopping along. Okay, so that's a very simple stochastic dynamics. And the dynamics, this Markov chain is realized in terms of trajectories, which I will call omega, which is the particle is in some site at some random time. It jumps to nearest nearest neighbor site and so on and so forth. So it's evolving. The configurations of the system are evolving, and that defines the trajectory after some total time t. Now you have stochastic dynamics realized in terms of stochastic trajectories, and if you want to understand dynamics, you need to quantify it in terms of observables of dynamics. I'm going to call those capital K of omega. So that's an observable of a dynamic. It's a function of the trajectory. And a very simple one is, for example, the number of jumps in a trajectory. So, trajectories are stochastics, and this trajectory observable is distributed. And of course, it is a Poisson process. I'm choosing this because it's very simple. So if you want to, quantify the statistics of the dynamics, understand the fluctuations of the dynamics in terms of that observable of trajectories, natural thing to look at is the probability to find a certain number of jumps in trajectories of a time length t. Yes, that's summing over probability. There is a certain probability for each trajectory, sum over all trajectories, a delta function of the observable taking a certain value, and modulo up to some caveats. The same information is contained in the moment generating function, which is essentially the Laplace transform of the probability, which it's if you take the derivative with respect to its argument, gives you the moments of the observable, in this case the total number of jumps. And of course, this is a Poisson process, so you can solve it exactly. So the probability is just Poisson function, and if you transform it, you can get this generating function, and it has an explicit form. And if you take long, the limit of long times, you can do Stirling on the factorial, and what you get is that the probability is exponential, is an exponential of time times some function that depends on the quantity of interest, the number of jumps divided by time. And similarly, the partition, this moment generating function is also exponential in time times some function that depends on its argument, the variable s, the field s. And this is a very elementary example of large deviations. In the limit of long time, the total number of jumps, it's an additive quantity. It's a random variable composed of summing up, the jumps along the trajectory. When time is large, very often under relatively general conditions, what one gets is that probabilities of the moment generating functions are exponential in the quantity that controls the size of the trajectory, in this case time, times some function that for the moment generating function, for the probability depends on the observable that one is considering, and for the moment generating function on a conjugate variable, the variable that appears in the moment generating function. Okay, and I mean, I've quoted here some physics literature on large deviations. Of course, there is also a very very extensive mathematical literature on it. So now, this can of course be generalized to any many-body dynamics, and I'm just made little picture here of some classical many-body system, where again one has stochastic dynamics and has trajectories and has observables of those trajectories, which in general are time-integrated quantities, time-integrated observables of trajectories, in the sense that typically they grow if they grow proportional to the length in time of the trajectory. One can define probabilities for the probability for that observable or the moment generating function, and at long times they will have large deviation forms. Yeah, they will be exponentials in time times some function in the case of the probability of the observable divided by time, or in the case of the moment generating function, which I'm trying to argue that contains the same information, is exponential in time times some function that depends on the variable s in this case. So now, What this defines is what I'm going to call a thermodynamics of trajectories. And why is that? Because we have a direct analogy with the equilibrium ensemble method that we use in statistical mechanics, to derive thermodynamics. So we have a parameter that controls the size of the system in standard equilibrium stat mech, it's volume. So here it's time. Time is the size of the trajectories. There is an extensive quantity, it's an order parameter if you want, or an observable, and that's what I'm calling K, the time integrated observable of a trajectory. And there is a conjugate field. So if you think of equilibrium, you can think of energy and inverse temperature, or magnetization and magnetic field. You have an order parameter distribution and a partition sum. And then in the large size limits, these are controlled respectively by an entropy density or a free energy density. And these two quantities that determine the properties of this probability and this moment generating function are also connected by Legendre transforms. Yeah. So this is the basic setup of equilibrium stat mech translated to trajectories. So that's the first thing I'm trying to emphasize. If one wants to study stochastic dynamics, one has to do so using a framework which is analogous to that of equilibrium stat mech, but which is applied to ensembles of trajectories. Those are the objects of interest. So then, like in usual stat mech, what we try to do is to calculate the partition sum. And in particular, we try to calculate the free energy density. So this large deviation function theta of S is like a free energy density for trajectories. And just like in standard equilibrium stat mech, we try to the aim is to calculate free energies, because free energies tell us about phases and phase transitions through their singularities. So now, a little bit of detail how to do this, and most of my talk will be about calculating efficiently these kind of quantities in various problems and settings. So now, so what's this dynamical partition sum? It's a sum over all trajectories, the probability of the trajectories, and the exponential e to the minus s, the observable of interest. Yeah, so it's a moment generating function for that observable, but it has the shape of a partition sum. So now some definitions. I'm calling the trajectory ensemble the set of trajectories and their probabilities as they come from the dynamics. And the dynamics, this I said this is continuous time Markov dynamics. The dynamics is generated by a Markov generator. I will call it, capital W, which has the usual form. It has off-diagonal terms. It's an operator that acts on probability vectors, and it has off-diagonal terms composed by the that's encode all the transitions, and these transitions have rates for transitions between any two distinct configurations, and then has and that's and those are positive because the rates are positive, and then it has a diagonal part which is negative that encodes the escape rate. So the dynamics is the system is in some configuration, and it will escape with a random time which is exponentially distributed with a rate given by its escape rate, and then it will make a transition to other configurations through transition rates that are given by these W's xy. Okay, so now the ensemble of trajectories generated by W, is the set of possible trajectories with their probabilities. If one multiplies those probabilities by these exponential functions, one defines what I'm going to call the tilted ensemble. One by hand is changing the weight of the trajectories given by the natural dynamics exponentially in the observable. And that's, as I will show a bit later, and this is important, that ensemble is quote unquote generated by a different operator, an operator that's related to the Markov generator, an operator which in general is not stochastic. So this is a stochastic operator, conserves probability and so on. And the deformation is not stochastic and encodes the object whose statistics one is trying to compute. Yeah. And now the interesting, and obvious fact when, and you say it a little bit later in more detail, is that the free energy function, this large deviation function, which is a free energy for trajectories, which controls the probabilities, and in this case, the moment generating function at long times, is nothing else than the largest eigenvalue of this operator. So what this does is converts the problem of calculating a partition sum into the problem of maximizing an operator. Yeah, and this, you should be anticipating how this will connect to the standard methods for with tensor networks. And that's the first analogy. This is it's the same kind of problem of finding the ground state energy of a Hamiltonian, except that what one looks for to obtain this is the largest eigenvalue of this operator. Okay. And that's if continuing with the StatMech analogy, what you have is a partition sum, and this object defines the transfer matrix of that partition sum. And in the large parameter limit, which in here is a large time limit, the partition sum is dominated, of course, by the largest eigenvalue of that transfer matrix operator. Okay. And then some more notation that's relevant is that once, and I'll prove it in a second, once one understands that the partition sum is related to a transfer matrix given by this operator, the partition sum can be written in this way, in the way up here. It's some probability vector evolution, quote unquote, given by this tilted operator, and then what's called the flat state, which is just summing overall configurations. Yeah. And the other thing to note is that this, again, looks like a quantum partition sum, except that there is no trace. In stochastic dynamics, you always have boundaries. You have some vector that indicates the probability distribution of from which you start, of the configuration, how the configurations from which you start are distributed. Then you have evolution, given in this case by this, tilted because you're tilting, you're computing in effect the moment generating function for that quantity, and then you sum overall configurations. So there are two things. This looks like a quantum partition sum, but it has boundaries, and the left boundary is trivial. It's always the same. It's always a flat state. And this is related to the fact that in classical stochastics, expectation values, and this is an expectation value, are linear in the probabilities. They are not bilinear as in quantum mechanics. Okay? But other than that, there are, if you want, two analogies here. One which is, well, both are very direct. The first one is this statistical mechanics of trajectories, partition sums, free energies, etc., for ensembles of trajectories. And the second one is that the calculations that one wants to do are very similar to kind of things that one is used to doing in quantum mechanics, except with these sometimes subtle but important differences. Any questions up to here? Well, I hope it is more or less clear, but if not, just stop and ask me. So that's the first piece of background I wanted to give you. The second one is on kinetically constrained models. I want to just pick these models because they're interesting per se for many reasons in different fields, and I will use them as examples to calculate the kind of things I was just discussing using the methods, the MPS methods I'll discuss in the next section. So once again, I'm considering classical stochastic systems. So here you have a master equation, probability vector evolves, dynamically evolves, and dynamic evolution, and the evolution is generated by the Markov generator, and that will give you the probability vector later. This is the master equation. And I was talking before about the Markov generator. Here is a specific one for the class of models I will be discussing. So imagine kind of textbook problem, undergraduate problem, just Monte Carlo. Well, this is continuous time Monte Carlo, but never mind. Monte Carlo of a collection of Ising spins in a one-dimensional lattice which are non-interacting. Yeah, and imagine furthermore that that's temperature is infinite. So you can flip up spins, up or down spins, and with the same rate. So then the dynamics is each spin can flip up and down with a rate that's which is the same. And this I will call the unconstrained problem. And the generator looks like this. It's it's a sum over every spin, the operator, the off-diagonal operator that gives you the spin flips, and this is like a sigma x in Pauli sigma x, minus 1. The escape rate would be 1, and everything's multiplied by some rate, which is a constant. Yep. So it's a totally trivial problem. On the left, you have a trajectory. So here is space, here is time. And what you see is that the trajectory looks like white noise. Sure enough, because you're flipping spin independently, there are no static correlations, there are no dynamical correlations. The trajectories look kind of featureless, and that's what they are. And sure enough, this operator annihilates a state, which happens to be like the flat state, but coming, Bragg would be a ket, which is just the sum of all configurations, an infinite temperature probability vector. All configurations are equally likely, and it's very easy to see that this is a product state of local states which have sigma x equal to 1. So if you apply this, you annihilate it. Yeah. And sure enough, if you have an equilibrium trajectory like this one, if you look at a typical configuration, it looks completely disordered. So now, let's change the rate from being a constant to being a function, to being an operator valued. Yeah, and this I will call a constraint. So this problem is, is very similar to the one before. You're flipping spins, but now you are not flipping them independently, because a flip of the spin the rate will be given by the value of a neighbor in this way of writing. And this happens to be called the East model. It's a very simple model. It's super relevant for glasses. So, and this one model I'll be using throughout. So now the rates, what the constraint encodes is the following, is that to flip a spin up or down, and here we have sigma x, so there is equal probability to flip it up or down if it can be flipped. A spin can be flipped if the neighbor is up. So this rightmost spin can only flip if the neighbor is up. So the neighbor up facilitates the flip of a spin to the east. That's the origin of the name. But if the leftmost neighbor is down, no flip can occur, neither up or down, nor down. Yep. So now, modulo some details that I'll come to. This operator also annihilates the same equilibrium state as before. The infinite temperature featureless probability vector. Yeah. So the statics of this the static properties, stationary properties of these dynamics is exactly the same as before. But you can see immediately that a trajectory looks completely different. These trajectories of the unconstrained problem were featureless, and these trajectories are featureful. Yeah. And the reason is that a model like this one, due to the constraints, has dynamical correlations that do not show any signature in the statics. And that's why it's important for glasses, because glasses have that property that the statics look relatively simple and the dynamics are slow and complex. So now, the basic thing that you see here is in these trajectories, you have spin ups are black and spin downs are white. And there are these very large regions, these bubbles in space-time where nothing is happening. So it's almost like a coexistence in the dynamics. There are regions where there is a lot of dynamics, and there are regions where there are little dynamics, an active-inactive coexistence in the jargon. Okay, so this it has been known for a long time. And there are variants, you can change the constraints, you can put a constraint where, you can flip if either spin is up. This is called the Fredrickson-Anderson model. It's the original kinetically constrained model. It also has interesting, slightly different trajectories, the same property that the stationary state is trivial. And the people have been looking, at a quantum coherent version of another constraint, the Pxp constraint. It comes from, it's originally studied, as far as I know, by Fendley and others 15 years ago, but then it's reimmersed in the context of Rydberg's. And one can think of a constraint like the Pxp where you need both neighbors. It's a strong constraint. You need both neighbors in a specific state down, in order to be able to flip. And the constraint is stronger. The dynamics is a little bit less striking, the stochastic dynamics. And I won't discuss this, but the reason is that the constraint in the Pxp breaks ergodicity very, very strongly. The state of space is broken. Sometimes they call it shattered into many disconnected components. So what's left of the motion inside is kind of not very interesting. Well, these slightly weaker constraints, they only have one state. You have periodic boundaries, which is the old zero state, which is decoupled, but everything else is here, and the dynamics here is interesting, as I was showing there and there. Okay. So there's kinetic constraints, long introduction to that. So now let's connect the two things, the thermodynamics of trajectories I was talking about. So now the generator is specifically the one of the East model, and the observable is the number of spin flips in that's usually called the dynamical activity. So then the partition sum, well, the partition sum, it's the probability of a sum over all trajectory, probability of trajectories, and exponential e to minus s, the number of spin flips. So now the sum over all the trajectories are trajectories which have any number of spin flips, any number of jumps occurring at any possible time, and the probability of the trajectory is given by a sequence of the exponential of the escape rate, applying a jump, jump, exponential escape rate. Okay, so this is what it is. This is the Dyson series expansion of the exponential of the generator. And if one wants to compute, the exponential e to the minus s, the number of jumps, every time there is a jump, there is an e to the minus s, this red factor I put there. This, by the way, start to connect it to CMPS, and if I have time, I'll mention it. So then, then we see that we can absorb in J, these factors of e to the minus s, and that defines the tilted operator. Yeah. So the original operator had R and J. R was this one times that, and the J was this times that, or the set of those. If we absorb an e to the minus s on the J, we define the tilted operator, and written explicitly, not not compactly, is this is the tilted generator. It's the same as the original one, except that all the off-diagonal terms have an e to the minus s factor. And that's called the tilted generator. So then, what we want is, we want to, as I said before, compute this object either at long times or then at finite times, and this object is generated by this deformed operator. So now, any questions up to there? Now I'm going to go through some of this concrete results. Okay, so again, if you want, you can stop me. So now let's focus on this East model, and let me show you how, what for you will be very standard MPS methods can prove to be really powerful in this setting. So now I will consider this model a slightly generalization, just because I want to show some results in this generalized case, which is at infinite temperature, in the sense you can flip spins up and down, but the spins up carry an energy which is larger than the one of the spins down. So the rate to flip up is it's given by this quantity c, and the rate to flip down is 1 minus c. Yeah, it says this is a magnetic field, and then it costs energy to flip up, but still the constraint is you can only flip if your neighbor is in the up state. So then the generator is basically the same as before, except that now you have a sigma plus with one rate and a sigma minus with another rate. You cannot add them up to the case I was talking about before has c equal a half. So this term would be equal to that one. But again, it's an off-diagonal part that makes the jumps minus a diagonal part that's escape rate. And we'll consider, for just technical reasons, open boundaries. So there is a one that's fixed on the left, and then you have anything. So you're always in this every configuration is connected by the dynamics because of this one on the left. And the equilibrium state is just a product state. It's not the complete flat state because ones are more expensive than zeros, but what you have is you have this mixture at every site, and then the direct product of the product over everything. So it's a product state. So now this system has detailed balance. So if you have detailed balance, you can define a Hermitian operator, and I'm going to change the sign by multiplying with square roots of a diagonal matrix, whose entries are the probability, the equilibrium probability. So if you do that, and trust me, this calculation is straightforward, then this operator, which is similar to that one through these similarity transformations, has essentially the same properties, except that it's Hermitian, looks like this. So it's a sigma x. So you've made this term, which was non-Hermitian, into Hermitian, and this term is diagonal, so stays the same. Yep. Okay. So it's a relatively, simple operator. It looks like the Hamiltonian of a spin chain. Yep. It has, this kinetic term with sigma x and the constraint n times sigma x, and it has some potential energy term with n's and n's times constants and n's times 1 times n. And all we want to do is what I told you before. We want to calculate the large deviation function, this scaled cumulant generating function, sometimes it's called. It's like a free energy, and it's nothing else than the ground state energy of this operator. And then there will be, this operator will have a ground state vector, and that will give us the left and right leading eigenvectors of the tilted generator. I'm calling them L and R. It's just the ground state multiplied by the matrices that defined the similarity transformation. Okay, so then and then just we now turn the crank of MPS. And I will just show you the results. To calculate. So what we want to get the ground state of some spin chain that is a Hermitian version of the generator of the stochastic dynamics. And not surprising probably to you, but certainly surprising to someone like me and people in this area looks like a miracle. You can get through, by just, using essentially the MRG, extremely precise results, which are very, very hard to get any other way. And what you find is the following, and this here I'm showing in a log scale, this large deviation function, so minus the ground state energy. And what you see immediately is you have two branches, one that's essentially so one that's straight in this representation, and a second branch, and they cross, and the crossing is moving leftwards as the system size is getting larger, and this is achieved to very good precision with bond dimension up to 100, let's say. Yeah, so these are things that you probably have seen in the context of spin chains many times. And the derivative, minus the derivative, is like a free energy. And if you take the derivative with respect to the, to the variable, which is a field of a free energy, what you get is an average observable. And in this case, the average observable is the it's the average activity, average number of spin flips in trajectories if you've tilted the ensemble of trajectories by that exponential I showed you before. And sure enough, when you have two eigenvalues that cross, and the cross becomes progressively sharp as the system size increases, what you have is two distinct levels for the derivative. And what you end up having is a progressively sharper and sharper jump between two values. And what this is a first order phase transition. Yeah, this defines a first order transition. But this transition, what it's encoding is a phase transition in the space of trajectories. So the dynamics generates trajectories, an ensemble of trajectories, and this ensemble has a first order transition, and that transition is getting closer and closer to s equal to 0 as the system size increases. Yeah, and this, while this was known, it was never shown to this accuracy and until this this MPS approach was used. So I mean, what this allows to do lots of things. It allows to calculate, precise scaling of, precise finite size scaling of the location of this transition. This transition is moving. So what one can show is that the location of the transition goes as n to minus some power. And it was speculated theoretically that power could be 1. I mean, what you do it precisely in this way, which is better than anyone could do it before, and you see that this power is larger than 1. So that's a relevant result that you couldn't have gotten otherwise. And then you can do the kind of things that you always do. You can take the ground state vector and inspect its structure, the structure of, in this case, of configuration. For example, what are the density profiles? What's the density as a function of space in the dominant states, depending on the value of S. So now, when S is equal to 0, the state is the equilibrium state, which I said is a product state and is structureless. Yeah. When S is positive, remember there is an e to the minus s number of jumps. What you're promoting there is trajectories that have very few jumps, and the state that you get is essentially empty, or is exponentially localized. You have the 1, and then you go eventually to 0, everything's 0, and it's exponentially localized. And when S is negative, you are exploring the set of trajectories which have number of spin flips, which is much larger than typical. So if you do that, what you see, and this is why I wanted to do it for C different than a half, so that's what would quote unquote be lower temperatures, is that as you're moving negative in S, which is in this direction, when you start to generate is structure in the dominant configurations have structure, have correlations in space. And the regions that you have, the reason that you have correlations in space is, remember, you need ones to flip. So even if typically you would like to have a very low concentration of up spins, if you are filtering the dynamics according to high number of spin flips, the dominant, those trajectories have configurations which have a larger occupation, first of all, and secondly, distribute the up spins such that they are evenly distributed, and this maximizes the number of spin flips. So as one is exploring fluctuations in the dynamics, which have much larger number of spin flips than typical, what you also see is that there is a singular change in the characteristics of the configurations that you visit, and this is encoded in the largest eigenvalue of this tilted generator or Hamiltonian. Okay, so that's the first thing. I want to say 2 more things. And by the way, and so I've been talking. I've been using the language of this free energy like function theta, which depends on what's sometimes called the counting field, which is the conjugate of the actual observable. So now by Legendre transform, one can take this and that, and with that information construct the Legendre transform. The Legendre transform gives you the probability. So here I'm plotting the logarithm, divided by time, the logarithm of the probability of number of spin flips in a trajectory. This is something you can go, in principle, you can go directly and measure. You run your dynamics and you compute the histogram of number of spin flips. And then what you see is, remember, the trajectories look like these, typical trajectories. And what you see is that, okay, there is an average value for the number of spin flips that might be here. And if that's, the number of spin flips in trajectories, the activity was distributed as a Gaussian, this would be the distribution. But I told you that there is an underlying first order phase transition that we saw when discussing in terms of this free energy like quantity. And sure enough, what you see is that the probability distribution becomes extremely flat. The larger the system size, the flatter it becomes, and eventually it has a shape almost like, like a square, if you want. And what this is saying is that even if this is the dominant behavior, there is almost equally likely probability of having behavior such that there are essentially 0 number of spin flips, and everything in between. So this is the Maxwell construct of a first order transition. You have 2 phases. You have an active phase, which is living here. You have an inactive phase, which is living there, and a Maxwell construct. And you uncover this by calculating this, this probability distribution the way I've told you before. And that's why what one runs trajectories that have typically this number of spin flips, one says phase separation between two regions, because one region would belong to that phase and another region would belong to another phase. So these are really like bubbles, but in space and time. Okay. So now, and final thing, I talked about the Pxp. So these are results by Chepig and Mila that if you translate them, gives you, this same rate function, but for the Pxp model. I told you Pxp model has less interesting statistics, and sure enough, there is some singularity, but it's way in the tails of the probability distribution. Well, in this problem, the singularity is competing with the typical behavior. Okay. So then let me say a couple more things. I have 38 minutes here, Frank. So you tell me if I'm overrunning or not.
No, you're doing perfect.
Okay. Okay. So that was long times. Long times is easier because at long times you only need to find this leading eigenvalue. Yeah. But now let's consider finite times. So at finite times, there is a partition sum that one would like to calculate. This is what encodes all the statistics of your observable and therefore your trajectories. And only at long times it becomes dominated by a leading eigenvalue. Just, it reminds one of a quantum partition sum. What can we say about finite times? These are much more difficult problem. In principle, you need all the spectrum. So now what one can do is just to try to run what in quantum one would say it's imaginary time dynamics. It's almost like calculating a thermal partition sum if you want. And the trick basically is to do the following: is to take the initial distribution, which could be the equilibrium distribution of the problem, and then split the state into two using a projection. So project it on the leading eigenstate, which one knows from the DMRG I was explaining before. So that part of the state is easy to evolve because we know everything. It just evolved according to the leading eigenvalue that we calculated in the previous section. And then the rest, which is 1 minus that projector, the rest of the vector, one can evolve with some standard method like TEBD. Yeah. And then you put them together. And what you get is you get the evolution, you get this part, you get the initial state evolved up to some arbitrary time t, not necessarily a long time. At long times would only be this, but at arbitrary times we'll have a contribution here, and here it's put together. Yeah. And remember, I'm using the language of the stochastics, but by detail balance we can make everything Hermitian, and you can write it this, as you would in a imaginary time quantum problem. And then you can compare it. I mean, you wouldn't be this audience, I guess, won't be surprised, but other audiences would, find surprising. And this is just to check that if you do it with exact diagonalization and you do this method, these two quantities coincide. But now we can do it for large sizes, and this is the kind of results you get. Yeah. So now what we have is we have the same problem as before here. This is the axis S, and I'm plotting the log of the partition sum, which is the free energy. And here we have the inverse of time. So before at infinite time, we were operating here. This is where the eigenvalue dominated, and there was a singularity which was moving towards 0 with system size. So this is a very small value of S for this system size, which is about 100. Yeah. And if time gets shorter, the transition, first of all, the transition strictly disappears. Yeah. Because one needs infinite time to have a strict singularity. But there is a whole regime where the transition dominates. This is a little bit like what happens at finite temperature with a quantum phase transition. But remember, this is classical, stochastic, and this is a dynamical transition. And the transition becomes a crossover. The crossover is still sharp, and it's moving to larger values of S, and eventually becomes very diffuse. Yeah. And just like we did before, the power of this is now we can calculate this object in principle for all times with pretty good precision, at least, for the state of the art. And again, by doing a Legendre transform, one can write the logarithm of the probability of the observable. And what one says is that for large times, it has the shape of a first order transition that we were discussing before with a, this is minus the log. So it's like the probability, the log of the probability the other way around. It's called the rate function. So for large times where there is, strictly a transition, you have, and for times in that regime where you have a crossover, but it's still appreciable. You have this very non-Gaussian distribution with very large fluctuations, and then when you go to shorter times, progressively the fluctuations become less interesting, and this probability distribution becomes more Gaussian. Yeah, and from the point of view of stochastics, this has a lot of interesting aspects. First of all, this ability to calculate these objects for finite time. The second one is that one is directly calculating the partition sum. This one is not sampling trajectories. This is like summing over infinitely many trajectories. So it's very it's very appealing in that sense. And the other thing that one can do, of course, if you can do this precisely, before we could do finite size scaling, in the infinite time limit with the eigenvalue. Now we can do both finite time and size scaling. So so this is the location of the crossover, quote unquote, transition as a function of time or inverse time for various sizes. And then, you can collapse it all in such a way that you understand how these scales, the finite size scaling of the location of the transition, both with size and time. And again, one can compare to, semi-rigorous results that exist there. Okay. So, okay, the final thing I want to say, so two things. Long times, it's an eigenvalue problem. MPS works like a treat. Finite times, it's not an eigenvalue problem, but one can still apply this method. It's like calculating partition sums, and it works super well as well. The third one is, can one find optimal dynamics? Yeah, let me use the last 4 or 5 minutes to discuss this. So I was saying that the object of interest is this dynamical partition sum, which is the sum over all trajectories in this tilted ensemble, yeah, which is generated by this W of S. So what's the problem? If you think of this, if you run dynamics, you generate trajectories, but you would like, and the trajectories come with this probability. But what you would like to explore is trajectories which have this probability exponentially tilted. So going back to some of these figures, what you'd like to do is, normal dynamics would give you the trajectories here, typically. But you would like to, by changing S, in effect, explore the tails of the distribution, explore trajectories which may occur with very low probability. Yeah. So now, how does one do that? It's not very efficient just to run dynamics. You're trying to look at objects which are exponentially suppressed in space and in time. Very, very suppressed. And then you say, well, there is an operator that generates them, but it's not a stochastic operator. It's just a deformation. This is an object you can study, but you cannot produce use it to generate. You cannot run a Monte Carlo starting from here. So the question is the following. Is there a stochastic operator, W tilde, whose probabilities, you would run dynamics because it's stochastic, defines a Monte Carlo if you want, and the probabilities are precisely the probabilities of this tilted ensemble, these exponentially tilted probabilities, and of course normalized by the partition sum. So that's the question, and the answer is yes. And this is what's called the Doob transform. The Doob transform happens to be a gauge transform in the MPS language, but that's the CMPS business that I can mention later. And at long times, the Doob transform can be written explicitly if you know the left leading eigenvector of the tilted generator, and the eigenvalues, so the ground state, function, and energy in the Hermitian language, then you can write an operator, and that operator generates these rare trajectories on demand. It makes the rare trajectories typical. Yeah. Okay. So it's the optimal way to sample these rare events. What's the problem? You need to know that object and you need to know that object. And what's the good thing is that, the MPS I was telling you about, at the beginning, you know, from there we know precisely this leading eigenvalue and the leading eigenvectors. So the question is, can we take that information that was coming from minimizing, you know, with these MPS techniques, this tilted generator to construct, you know, these optimal dynamics? And the answer is yes. And then, you know, there's some technical, you know, there's some, you know, technical details on how you do it, but, you know, basically what one needs, if, you know, this optimal operator, this Doob generator, is a stochastic dynamics that generates these rare trajectories on demand, has transition rates, and these transition rates, the transition rates depend on the ratio of elements of the leading eigenvector. Yeah, so this is like, you know, the ground state, or is a ground state wave function squared for Hermitian problems, evaluated at the two configurations that you're jumping between. And then for the escape rates, you need to know the ground state energy, you know, this leading eigenvalue. And, you know, with some, you know, smartness, like the, you know, in this case, Lux, of course, was the one who figured it out. You can use the solution of you know, this MPS very accurate approximation to these objects to define a stochastic dynamics, and then you run the dynamics, and what you see is that in the case of the East model again, so what you can do is typical dynamics occurs here, so that's what you would run in your Monte Carlo, but you would like to go to regimes where you have an activity which is either much larger than typical or much smaller than typical. You can do it, you know, just by in the way I explained, and then you generate trajectories. The trajectories here look very dense in the way I explained before, because what you want to have is lots of excitations, much more than typical, to be able to move a lot. And on this side, you want to move very little, so it's basically empty. The trajectory is essentially empty. And, you know, these kind of trajectories you would never ever get, because they are suppressed exponentially in space and time is supposed to go to, you know, to be, you know, large. But here you just generate them on demand. And then similarly, you can do it for other models, other actually constrained models, like the simple exclusion process is a, you know, hardcore particles hopping on a lattice. You can play exactly the same game. And then what you see is that for dynamics, which is very active, you know, the particles try to arrange to be as far apart from each other as they can while conserving the density, and that gives them the most room for motion. So that maximizes motion, while for the SEP has also an active-inactive first-order transition, as I described before. On the other side of the transition, the dynamics is such that these rare trajectories are such that all particles accumulate on one side, and therefore motion is only allowed on the boundary, and this minimizes the amount of motion. So that's, you know, basically what I wanted to tell you. You know, I'm running out of time, so I'll skip this CMPS part, and I give you, you know, this is what I told you. That's, you know, I told you about rare events and large deviations and constraint models. And then the bulk of this was, you know, how one can, you know, solve essentially numerically, you know, these problems, certainly in one dimension, using these tensor network techniques. And I will stop there. Thanks.
Thanks a lot, Juan, for this very interesting talk that is also pretty orthogonal to all the other talks that we have seen, and that makes it so cool, actually. So are there any questions?
So maybe, is there any chance that you can say a few words about this last part, the relation with CMPS?
Yeah, and it will really be words, because I just want to draw the kind of the analogy, and it's, you know, it goes a little bit beyond, you know, just words. But so this is the only slide I prepared. What I wanted to say was the following: is that so if one thinks about trajectories, the ensemble of trajectories can be encoded in a vector. Yeah. And that vector can be the vector can have components, you know, so can have components which are the probability for each trajectory. Yeah, so you have some, you know, some abstract space where where each direction is, it's a different trajectory. So then you can build a vector where, each component is a probability of that trajectory. Okay. And then this is what it is. So it's trajectories are random objects. I can construct a probability vector on trajectories. So now it so happens that this vector is a classical CMPS. Yeah, in the sense that it's built out. Why do I say that? Because what I can think of is the following. I can say the probability of a trajectory is this sequence of operators. Yeah, a trajectory is defined by a number of jumps and when those jumps occur. And let's forget about different kinds of jumps. So that's like an amplitude of a CM, or that's analogous to an amplitude of a CMPS, because you're multiplying operators. It's like a train of operators, and that defines, in this case, the probability, the amplitude. And then there is, so in the language I'm using, the physical space is the space of that vector and the space on which these operators, the escape rate and the jump operators of the Markov matrix act. And then there is an auxiliary space which encodes the trajectory when the jumps occurred. Yeah. So, and of course, we have the experts in the audience, and I'm not one, but I'm saying that this looks like a CMPS. That's the first thing. And this vector is normalized. Yeah. If I multiply by the left by the corresponding flat state, which means if I sum over all trajectories, this vector, that's summing those probabilities, so that's normalized. So what I'm saying is that an ensemble of trajectories is encoded in a CMPS of trajectories that are continuous time Markov process. So now if I tilt the ensemble, that means that I'm just multiplying by this e to the minus s every jump. Yeah. So if I tilt the ensemble, which is the same as summing over all trajectories, probability of a trajectory e to the minus sk of that trajectory, and then here I put the vector that denotes the trajectory, the unit vector that denotes the trajectory. Well, when written is the same as before, except that now I have all these factors of e to the minus s. Yeah. So now I've encoded what's called the S ensemble, the tilted ensemble of trajectories, in another vector. But now this vector does not have units norm. Yeah, it does not conserve probability, because the norm of that vector is precisely this partition sum. Yeah. So then, I mean, this is just a picture, but basically this was the original ensemble. This is this one. When I tilt, I get another vector, which is this one. And this vector is not normalized and it's not written in terms of operators which define a stochastic dynamics. It's just this tilted generator. But then I can rotate that vector because I can insert identities, g to the minus 1, g to the minus 1, g to the minus 1, which might depend on time, these g's, yeah? And so on and so forth. And that's what you would call in MPS a gauge transformation, right? So basically you can keep the vector as it is, you rotate it, maybe you change the length, that doesn't really matter, but it's basically the same vector described differently. Yeah. And that's what it's called, this Doob transform in the stochastic literature and in the recent, the recent literature on large deviations and so on. But for MPS it's just, it's just a gauge transformation. Okay. So, I mean, is this useful? Well, this is useful conceptually because it's kind of compact, a compact way of defining this. The other thing that happens is that it makes calculating properties of operators of trajectories, this becomes something like that, right? So it's like, so now this complicated, apparently, properties, expectation values of operators of trajectories is really calculating expectation values in states like this or like that or like this one. Yeah. And, I think this is the same. And because it's the same, I think, at least from one end, one can borrow all the techniques that exist in the other. And maybe there is some backflow as well of ideas. That's all I wanted to say. Well, sorry, it was a long answer to your question.
But well, maybe I have a question with respect to this. So of course, the space that you have normally in a CMPS is now the time in your case, but But that means it's still a single particle kind of object. No, it's like a non-equilibrium zero-dimensional system. And I thought you were interested in actually one-dimensional kind of systems. So
okay. Let's and maybe I get this wrong, but this is my physical space. It lives here. Yeah. So for me, this object lives in physical space.
And this is like, what is the Hilbert space associated to P0? So it's like a many body system, or is it?
Oh yeah. This is a. I mean, these are probability vectors, but this is a probability vector on a many body system. Yeah, this lives on 2 to the n for n spins.
Yeah, indeed. Yeah.
Yeah, and then these matrices act on 2 to the n.
Yeah. Okay.
Yeah, and then this one is the timeline. And this is like this is excitations on some vacuum, and these excitations, it's continuous because these times could be anything, and there could be a label mu1, mu2, whatever. If there are different kinds of jumps, you want to identify when it happens and which jump it is.
Yeah, but that's probably why it's not so easy to actually do calculations with this, because the matrices themselves have to be exponentially large, and that's typically, of course, not what is done in the CMPS language.
Oh, that's true, but remember that these are trajectories, and trajectories I can sample by running Monte Carlo.
Okay, yeah, and that is possible indeed. Yeah.
So then I can kind of reconstruct this exponential complexity by running trajectories and adding up like that.
Yeah, indeed. Yeah.
So all I'm saying is that everything I was talking about before falls into this, into this formalism. Whether that's practical or not, I don't know. But I think it's an interest. I think it's interesting.
Yeah.
Yeah.
Maybe a similar question, actually. So you mainly talked about one-dimensional stochastic or system. So what happens in higher dimensions? Have you checked this, or has is there really different physics going on there?
Okay, two things. First of all, I forgot. I had them here, but I should have mentioned that I think you had Garnet Chan giving a talk about something else, but his group has been thinking about similar ideas for SEPs, for simple extrusion processes, and thinking about fluctuations of time integrated currents mostly, and they've looked at 2D. Yeah. So now, I mean, I don't need to tell you how much more complicated it is to do these things in higher dimension than one. The physics of constrained dynamics, of course, there are details which are important and different depending on dimensions, but the overall physics is not different. So these transitions I've been talking about, these first order transitions in these constrained models happen in all essentially happen in all dimensions. With the details change, but not the qualitative aspects. So now, how much one can uncover that with tensor network techniques, it's a really interesting question. Yeah. And it would be good to do it. Yeah. That I cannot say more than that.
Okay, thanks. So are there any other questions?
Maybe I have a question. So for this Pxp model, I mean, this is often looked at in terms of Rydberg atom problems, but there we are looking at real-time evolution. And
yeah, this is
in general, right? But from looking at your SEPs, is there something that we can, like, learning something about the SEP? Is it something that we can predict about the real-time dynamics of the model?
Okay, I've written papers. We've written papers with Mari Carmen on this, on taking the same generators like this one and running them with unitary dynamics. And those papers always start with some words about, the stochastic dynamics, which is imaginary time, has all these interesting properties. Maybe the unitary dynamics has interesting properties, and they do. And to an extent, some of those things are connected, and they are connected by, by the kind of states you can construct. How these states disconnect, the kinetic energy connects or doesn't connect configurations, and that you can then relate to resonances, etc., etc. I think there is something there more than what we've said, but I found it hard to pin down exactly what it would be. And the reason is that stochastic dynamics is ground states, imaginary time, ground state and low-lying states. And this, unitary, thermalization is a whole spectrum. But there seems to be something in this system. I'm referring back to those papers. There seems to be something in operators of this kind where it's not just the ground states and around the ground state where there's something interesting is going on, but throughout the spectrum. But it's hard to say it more systematically than kind of studying case by case at the moment.
And actually, one potentially and partly related question. I mean, if we would take a system with a conserved quantity, if we have these kinetically constrained systems with maybe U1 quantum number, is there something interesting to say about transport properties?
I think the answer is yes. Yeah, because the direct answer I can give you is the SEP. Yeah, and the SEP has fluctuations in what I call activity, number of hops, and has very interesting, and has correlated strong fluctuations in the currents. And so so one relates to dynamics, the other one relates to transport, if you want. Yeah, and if you go to something more glassy like the models here, there are variants of these models which are glassy but conserve, for example, the density. And what happens is that if you have these large fluctuations where you're not moving, you're not transporting either. Yeah, that's all I can tell you.
Okay, thanks.
Maybe this is a good time, unless there's another. I see there's another question. Please, Simone.
Okay, so I have a question, which could be a question about language, but I'm not sure whether it's only language, but also content, because I'm not so educated about this notion of CMPS states, because what you are doing is basically, I mean, these Dyson series representations. I guess this these Dyson series representation. One of the sort of tools what you use is that these are really probabilistic representations in the sense that all matrix elements are positive.
Yeah.
And is that really sort of what you call a CMPS, or are CMPS something more general?
No. Well, maybe fraction.
That's a probabilistic representation, a space-time representation.
So in
where positivity is a great, tool.
100%. I mean, Simone, I fully agree. In the sense that for a CMPS, this is really a quantum state. Yeah, and therefore it doesn't have the limitations that this one has for being a probability.
Yeah.
So I think it's just the real positive version of CMPS. Having said that, and I think this is known from those original papers over there, CMPSs are analogous to the input-output formalism of open quantum systems. Yeah.
Okay.
And in that case, this is a quantum state, and the object that becomes positive is that the density matrix you build out of this, like this and that. Yeah. And in that case, you can connect, these operators to the operators that appear in the Lindbladian. That would be the generator of that dynamics. So,
okay, but you are studying in
that's not what I'm doing here.
Yes, in these type of questions, you are studying sort of very particular versions of that, which are probabilistic.
Yes,
which admit these probabilistic space-time representations.
Yes.
Mm-hmm.
So, I agree, and I'm not sure how this is useful in practice, but at least to me and to others, this has proven a useful framework to think about, to compactly think about these questions of trajectories. Yeah.
Yes. Thanks.
Thanks.
So maybe I have a last question, Juan. So what about continuum limits of these systems that you're looking at? Do they have well-defined continuum limits actually? Is there a field theory associated to your systems?
Yes and no. I mean, things like SEP, we know more or less what they are, but this East model has. So let me go back to the constraint models. Yeah. Sorry. I don't know how to do it otherwise. So I talked about these two, this East and this FA model. Yeah. The FA model has a continuous limit, which is the same limit as reaction, as a field theory that you would have for reaction diffusion, for a reaction diffusion problem, which is branching and coalescence. Yeah. And the reason is that, the effective dynamics of an up spin is diffusive in this problem, for reasons I can explain. It's relatively straightforward. This East model, and I'll say something else. This East model, because of the directional constraint, we tried, many other people tried, 10, 15 years ago, and no one really found a way to write a field theory for them. Yeah. So that's an interesting question, and maybe now there is an update to this, because these problems are are very close to fractons actually. Yeah, and this would be type 1 type 1 and type 2 fracton, and there are field theories for type 1 fractons, and I'm not surprised because there are field theories for that. So the other Frank might know more about this, but that's my view.
Yeah, but so I think the prevailing understanding for the moment of all these fracton phases is that they are basically field theories with defects. So they're like defect field theories, and actually both fracton type 1 and type 2 fit into that framework as
okay.
kind of quantum field theories. The quantum field theories with defects, but okay,
well, the first ones I saw were for this. Yeah, thanks. I'm out of date, but yeah. But the real problem, well, the answer is what people have devised it for this, we and others, and people have tried and failed for that one. Yeah.
Okay, unless there are any other urgent questions, let's thank Juan for this great talk, and I hope to see all of you back next month. Thanks a lot.